we present spacetime surface regularization for neural dynamic scene reconstruction. In the 4D surface reconstruction from monocular videos, which we reconstruct a dynamic scene, we reconstruct not just the geometry but also the dynamics of the scene simultaneously. However, 4D reconstruction is a highly ill-posed problem, and it often fails for two reasons. First, learning deformation is sensitive to topological variation and illumination change. Second, using the density representation, which has high degrees of freedom, could result in overfitting, floaters, and blurry reconstructions. To address the issue, we propose an algorithm, namely 4D regularization SDF, for spacetime surface regularization to improve the fidelity of neural rendering and reconstruction in dynamic scenes. On the HyperNerf dataset, a widely used real-world monocular video dataset, our method demonstrates the good quality of surface normal rendering as well as color rendering. Note that our method generates smoother and crisp reconstruction due to the regularizations we introduced in our paper. These are the other real-world results from the same HyperNerf dataset. Our method consistently reconstructs the crisp and clean surface normals, while the previous study generates reconstructions with a lot of noise on the surface. Normal even though the RGB video renderings it generates are comparable to ours. Our network represents the 4D spacetime domain as a combination of the static geometry in sign distance function and the deformation field. Our 4D regularization is applied to both the static sign distance function and the deformation field. Our regularizations consist of three components: total variation of curvature, absolute curvature, and the iconal loss. First of all, the total variation of curvature aims to limit the amount of change in curvature induced by motion. This regularization imposes local rigidity at different time steps. For example, given the curvature values at time 1 and time 2, the curvature values should stay the same if the object is rigid. Thus, by minimizing the difference in curvature values, we assume that objects move rigidly. Second, we define that the absolute curvature of the SDF is simply the L1 norm of the Hessian matrix. By minimizing the absolute curvature, we remove unnecessary curves or kinks in the reconstructions, making the surface as smooth as possible. We use the conventional iconal loss on the static sign distance function. The iconal loss enforces the gradient of the SDF to be valid by minimizing the deviation of the norm of the gradient from 1. Another important component of our algorithm is the surface sampling. The curvature values we use for regularizations should be sampled on the surface of objects as we impose the rigidity, flatness on the surface, not on the space around. We first sample points on the surface and apply augmentation on the samples. Finally, we apply the spacetime regularizations. Let's first go over the surface sampling. The signed distance function defines the distance to the closest surface. We use the gradient and the magnitude from the SDF to take gradient steps toward the closest surface from randomly initialized points in 4D space. We visualize the gradient steps here. Note that the samples converge to the surface of the objects after a few iterations. The second stage is temporal augmentation. We use the samples from the previous surface sampling stage and create corresponding pairs at different time steps. For each sampled point, we apply the deformation field and transform the sampled point to a corresponding point at different time. We do this augmentation in the continuous temporal space to make the space smooth temporally. Finally, we apply the space-time regularizations to these samples and minimize the total loss. The total loss consists of conventional rendering color loss, cycle consistency of deformation field, the iconal loss, and the regularization energy that consists of the total variation of curvature and absolute curvature. Using the regularizations and 4D SDF representation, our reconstruction shows high-fidelity reconstruction on the dynamic synthetic NERF dataset. Please visit our project website for more information. Thank you.